Hi everyone, this is VK. Welcome to Smid World. Here I am with another video. Welcome to Cement World. In this video, we'll learn about ESP, electrostatic precipitator, how it works, what is the working principle of the ESP. Working of electrostatic precipitator. An ESP works because of electrostatic attraction, like charges repels, unlike charged attraction. An ESP uses a high voltage electrostatic field to separate dust, fume, or mist from a gas stream. The precipitator consists of vertical parallel plates forming gas passes 12 to 16 inches. If you see in centimeters, 30 to 40 centimeters apart. Discharge electrodes are electrically isolated from the plates and suspended in rows between the gas passages. Every particle either has or can be given a charge, positive or negative. A high voltage system provides power to the discharge electrode to generate an electric field. The particulate entrained in the gas is charged while passing through the electric field. The particulate is then attracted to the grounded collector plate and forms a dust layer on the plate. Periodic wrapping separates the accumulated dust layer from both the collector plates and discharge electrodes. The dust layer released by the wrapping collects in the hoppers and is removed by material. Particle charging. Typically dry ESP with thin wires as discharge electrodes. Dry ESP having a thin wires as discharge electrodes, which are evenly spaced between the large plates called collection electrodes, which are grounded. An electrode is something that can conduct or transmit electricity. A negative high voltage pulsating direct current is applied to the discharge electrode, creating a negative electric field. See, you can hear the figure ESP electric field, inter-electrode region, the weakest and strongest in between. The field is stronger near the discharge electrode, weaker is the areas where the discharge and collection electrodes called the inter-electrode region, and weakest near the collection electrode. The particle charging process begins in the region around the discharge electrode. Free electron generation. The several things happens very rapidly in the small area around the discharge electrode. The applied voltage is increased until it produces a corona discharge, that is electric breakdown of the gas, so that it gets transformed into insulating to conducting state, which can be seen as luminous blue glow around the discharge electrode. The free electrons created by corona rapidly moves away from the negative electric field because it repels them. They move faster and faster away from the discharge electrode. This acceleration causes them to literally crash into gas molecules, bumping off electrons from the molecules. As a result of losing electron, the gas molecules become positively charged. That is, they become positive ions as shown in the figure. Thus, the gas molecules are ionized, electrons are liberated. This activity occurs very close to discharge electrodes. As shown in the above figure, this process continues, creating more and more free electrons and more positive ions. The name for all this electron generation activity is avalanche multiplication. The positive ions move toward and negative discharge electrodes, as the positive ions are 100 of times bigger than the tiny electrons. They move slowly, but they do pick up speed, and many of them collide right into the metal discharge electrode or the gas space around the wire, causing additional electrons to be knocked off. This is called secondary emission. Ionization of gas molecules. As electrons leave the strong electrical field around the discharge electrode, they start slowing down. In the interelectrode area, they are still repulsed by the discharge electrode, but to a lesser extent. They collide with the gas molecules in the interelectrode region also, but instead of violently colliding with them, the electrons bump up to gas molecules and are captured by them, as shown in the following figure. This imparts a negative charge to the gas molecules, creating negative gas ions. You can see in the picture the formation of negative gas ions in an interelectrode region. Because the ions are negative, they move in the direction opposite to the stronger negative field along the path of invisible electric field lines toward the collection electrode. These negative gas ions play a key role in capturing the dust particles, as explained in the following section. Charging of particles. The charging particles are traveling along in the gas stream. They encounter of the negative charged gas ions moving along the path of invisible electric field lines toward the collection electrode. The gas ions stick to the particles, impacting a negative charge to them. At first, the charge is fairly insignificant, as most particles are used compared to a gas molecule. But many gas ions can fit on a particle, and they do. Small particles can absorb tens of ions. Large particles can absorb tens of thousands of ions. Eventually, there are so many ions stuck to the particles. The particles emit their own negative electric field. When this happens, the negative field around the particle repels the negative gas ions, and no additional ions are required. This is called the saturation charge. Now the negatively charged particles are feeling the inescapable pull of electrostatic attraction. Bigger particles have a higher saturation charge, and consequently they are pulled more strongly to the collection plate. In other words, they move faster than smaller particles. Regardless of size, the particle encounter the grounded collection plate and stick to it because of adhesive and cohesive forces, as shown in the above figure. And more particles accumulate, they create a dust layer. This dust layer builds until it's somehow removed. Particle charging mechanisms. The particles are charged by negative gas ions by one of the two mechanisms, field charging or diffusion charging. In field charging, particles capture negatively charged gas ions as the ions move toward the grounded collection plate. Diffusion charging, as its name implies, depends on the random motion of gas ions to the charged particles. As shown in the above figure, in field charging, particles causes a local dislocation of the electric field as they enter the field. The negative gas ions traveling along the electric field lines collide with the particles and impact a charge of the gap. The ions continue to collide a particle until the charge on the particle is sufficient to divert the electric lines away from it. This prevents a new ions from colliding with a charged dust particle. When a particle no longer receives an ion charge, is said to be saturated. The saturated charged particle then migrate toward the collection electrode and are collected. Diffusion charging occurs due to the random Brownian motion of the negative gas ions. The movement of gas ions random motion is related to temperature. Higher the temperature, more the movement. The negative gas ions collide with the particles because of their random thermal motion and impart to a charge on particles. In case of very small particles, they do not cause local dislocation of the electric field. Thus, diffusion charging is the only mechanism by which very small particles become charged. The charged particles then migrate to the collection electrode. Each of these two charging mechanisms occurs to some extent depending on particle size. Field charging mechanism dominates for particles with a diameter greater than 1 micrometer and diffusion charging mechanism dominates for particles with a diameter lesser than 0.1 micrometer. The combination of these two charging mechanisms occurs for a particular range of between 0.2 and 0.1 micrometer is that in diameter. The third type of charging mechanism, which is responsible for very little particle charging, is electron charging. With this type of charging, fast moving free electrons that have not combined with gas and ions with the particular and impacted charge. Electric field strength. Because of the high electric field applied to the ESP. In the inter-electrode region, the negative gas ions migrate toward the grounded collection electrode. This forms a space charge, which is a stable concentration of negative gas ions in the inter-electrode region. The increase in the applied voltage to discharge electrode will increase the field strength and ion formation until spark power occurs. Spark power refers to internal sparking between the discharge and collection electrodes. It is sudden rush of localized electric current through the gas layer between the two electrodes. Sparking causes an immediate short-term collapse of electric field. For optimum efficiency, the electric field strength should be as high as possible. More especially, ESP should be operated at voltages high enough to cause some sparking, but not so high that collapse of the electric field occurs too frequently. The optimum ESP voltage is achieved by an automatic voltage control. The automatic voltage control varies the power to the transformer rectifier, set in the response to signals received from precipitator and from the transformer rectifier itself. The ideal AVC would produce the maximum collecting efficiency by holding the voltage on the precipitator electrodes at a valve just below their ever-changing spark power voltage. Since there is no way of determining the spark power voltage at any given time without allowing a spark to occur, the AVC commands increasing output from the TR set until a spark occurs. The spark signals the AVC to reset its command layer. The AVC again commands on the increasing output from this new starting point, and the cycle is repeated. The average spark power rate of optimum precipitator operation is between 50 and 100 sparks per minute. At this spark rate, the gain is efficiency associated with the increased voltage compensates for decreased gas ionization due to reduction of electric field. Particle collection. When a charged particle reaches the grounded collection electrode, the charge is slowly leaked to the grounded collection plate. A portion of the charge is retained and contributes to the intermolecular adhesive and cohesive forces that hold the particles onto the plates. Adhesive forces cause the particles to physically hold on to each other because of their dissimilar surfaces. Newly arrived particles are held to the collected particles by cohesive forces. Particles are attracted and held to each other molecularly. The dust layer is allowed to build up on the plate to desired thickness, and then the particle removal cycle is initiated. The particle removal: dust that has accumulated to certain thickness on the collection electrode is removed by process depending on the type of collection electrode. Tube type of collection electrodes are usually cleaned by water spray, and while plates type of collection electrodes are cleaned by either by water sprays or process called wrapping. What is the wrapping? Wrapping is a process whereby deposited dry particles are dislodged from the collection plates by sending mechanical impulse or vibrations to the plates. The precipitator plates are wrapped periodically while maintaining the continuous flue gases cleaning process. In other words, the plates are wrapped while the ESP is online. The gas flows continues through the precipitator and applied voltage remains constant. Plates are wrapped when the accumulated dust layer is relatively thick. This allows the dust layer to fall off. Plates are large aggregate sheets or clumps that fall by gravity into the hopper and eliminate. As the clumps fall downward, they are swept toward the outlet of the precipitator by the horizontal moving gas stream. If the clumps are too small, gravity is too slow to allow the clumps to reach the hopper before the gas stream carries them out to collector. From this reason, gravity settling is an important step in a particulate matter control in electrostatic precipitator. Dislodged dust falls from the plates to the hopper. Dust should be removed as soon as possible to avoid its packing. Packed dust is very difficult to remove. Dust. Most hoppers are emptied by some type of discharge device and then transported by a conveyor. In a precipitator, using liquid sprays to remove accumulated liquid or dust, the sludge collected in the holding basin at the bottom of the well. The sludge is then sent to petrol ponds or landfilling areas. Spraying occurs while the ESP is online and is done intermittently to remove the collected particles. Water is generally used as the spraying liquid. All liquids could be used if absorption of gaseous pollutants is also being accomplished.